So as Dave said, my name is Kevin. I'm part of the deployment strategy team at Neo. Most of what that means is I spend lots of time with our customers building hopefully big, cool, and exciting stuff. And today I'm going to walk you through the universe of Neo4j. This is kind of the part in the day where we kind of like browbeat you with like speeds and feeds and tell you about all the features and stuff. I will do my best to make it exciting and somewhat interesting and help walk you guys through our motivations for doing what we do and also hopefully where we see the market today and where we see the market going in the near intermediate future. So, click. Turning on your device helps. There we go. So we are going to hopefully connect lots and lots of dots very, very quickly. For those of you who came to the meetup last night, I gave the same disclaimer. There are kind of two schools of thought for presentation. One is like you take one topic and kind of dig very deeply into it and make sure that everyone like walks away knowing it. I'm not of that school of thought. I'm kind of like the spaghetti on the wall. We just throw everything up and we hopefully something catches and it makes a lot of sense. So we're going to move quickly and hopefully we're going to have a little bit of fun with it. So the things we're going to discuss today, first one is kind of like the big data ecosystem writ large. Neo4j, the database, how and why it works. And I think the interesting half is kind of beyond the database, what does it mean to build a graph native organization? And then from there, kind of what is our long-term vision for building a connected enterprise? So state of data in 2018. So I start with a somewhat depressing chart, depending on who you are. So this is actually from, I believe, the St. Louis Fed, where essentially they did a little bit of analysis on the tenure of an organization within the S&P 500. And essentially in the 1960s, if you were part of the S&P 500, on average, your tenure is about 60 years. And we've watched that really fall precipitously. Currently, I want to say it's like 15 years, and by 2030, it's supposed to be like sub 10. And so we're watching the market get frothier, and organizations are churning over more and more quickly. And kind of the fundamental question is always like, what happened? And my argument is that Amazon, Google, and Facebook happened, right? And I don't mean in that these organizations are sucking the air out of the competitive markets, but it's much more that they grokked the data problem before anyone else did. They figured out that there was a movement in data structure, there's a movement in paradigm, and because we're now in a data economy rather than a physical goods economy, they figured it out first, and they're causing this precipitous change in enterprises as well as the big data space writ large. And unfortunately, kind of the response that the market had in general was they doubled down on what they thought technology was like palpably. And so they said, oh, it's the apps that matter. It's the front end. Like if we make the edges rounder, then the users will like it and then we'll be competitive again. And it was really, hey, like what we want to do is we want a forklift, like startup culture. We'll be super agile, whatever that means. We'll go to the culture store and buy some and implement it. It'll be so much better. And then they're like, oh, and then we'll also hire my niece. She'll be our social media strategist. And if we tweet more, people will like us. And they fundamentally missed the whole, what's behind the scenes, what makes these great organizations great. And that is their ability to take data, structure it well, and access it well. And so there's a law, which means it's true. Conway's law is actually a social phenomena that was observed by, again, I think John Conway. And the argument is that people will build applications and software that mirrors the way in which they communicate. And you can extend that in the way that you communicate with your data and your data structures, and you can actually observe this in the real world, where obviously everyone knows what raw data is. Data points are great. We structure it in some fashion, and that we then access that to build our application. And so on the relational side, you can think of things like Excel. Like rows and columns, you can just feel it palpably in front of you. And then you look at things like, like a document store, like a JSON object, where I use that to hydrate, a web page, and you can feel, oh, the things that I'm storing together, being accessed together, renders really fast, and you kind of watch this, cross-sectionally. And my thesis is the type of application that we ought to be building is naturally very graphy. And so my thesis for this whole talk is that we've entered the era of the data structure, and not just the graph structure, but that we as developers and engineers need to be very thoughtful about how we're organizing our data and how that dictates the type of applications we get to build. And so to double click on the point, we can think of kind of Web 1.0 paradigms of hierarchies, a traditional supply chain that moves linearly, just raw information, and there's an underlying structure that maps to that. If we kind of reimagine these things, and we can actually observe this in the market, reimagining these data structures as graphs, we kind of move from like a hierarchy to an organization where we're able to start to capture things like, oh, though Jeff and I belong to different business units, we work together a lot, and that's meaningful. And then the type of work product we make together is very, very good, and so we want to capture that. We think of linear supply chain. I actually spent 2 weeks ago a considerable amount of time with an organization that's considered best in class in supply chain, and what they fundamentally realized or started to realize was that there's an incredible amount of dynamism to their supply chain, where they're not just making raw goods ABC, build intermediate goods get combined and they make finished product. There are all these amazing deltas that move between, oh, we're shipping this to this country, we have to make a specific sub-product for that. Oh, we need to push this back. How do we do impact analysis and see where the failure is happening along my supply chain? Can we trace it back to a raw good? And the last bit is information to knowledge, and also I think covered that deeply and profoundly, and I will not try to double click on that any deeper. And so to kind of observe the big data space, right? Relational will always, I think, fundamentally have a place in most stacks somewhere. It's very, very good at storage and retrieval. If I want to say, hey, Kevin's social security number is this, and kind of just shove it down somewhere, and I want to be able to say every time I get it back, Kevin's social is this, Kevin's social is this. This is kind of the process that both most relational and most NoSQL databases operate against. They're very, very good at storing and retrieving data quickly. We see kind of, I don't know if I'd call them a database. It's kind of like a CSV management system. But things like Hadoop, Spark, a lot of these like big data aggregators, what they're very, very good at is essentially telling you a summary in a reasonable amount of time, where they're able to look at something like a well beyond a petabyte, thousands of petabytes of data, and say, hey, by the way, I'm going to break up this job across 100,000 machines, and I'll tell you how many times this character shows up in all these documents. And the last bit is graph databases or things like Neo4j. We're optimized for revealing data in its context. So rather than saying, here's Kevin's social, respond with Kevin's social, but it'll be, hey, give me the context around this identifier. Hey, I have Kevin's social, who is this person? How is this connected? Am I trying to find fraud and say, hey, there are 2 people who are claiming this is their social? That context is important. And so, Neo, to continue to walk down the path, Neo is a database is purpose-built for connected data, and we'll talk a little bit more about what it means to be a platform built for that as well. And so, a brief history of data. Right. And so, in early 1980s, we watched that there's this interesting parallelism that occurs where anytime there's a big shift in the compute market, essentially data and databases have to kind of mirror along, and you can argue chicken or egg there, but kind of the movement toward the organization of things is client server. It's kind of when IBM and Oracle came to power. They kind of sucked the air out of the market when you had object databases and all these other things. NoSQL is God. And the compute we were doing was relatively tiny RAM. I looked it up. I think like a typical box of like between 1 and 16 megabytes of RAM. Paper was still kind of our predominant storage method, and we have spinning platters and sequential I/O for everything. So there's not a lot of dynamism you can build into your systems. We watched consumer internet happen, and we went from dealing with like the data within a singular organization to just the data, right? And so now we have gigs of RAM. SSDs are still prohibitively expensive, but it's giving us a little bit more speed. We're doing lots and lots of batch compute. And the coolest thing I think that kind of came through was the move from super specialized like Exadata boxes to commodity hardware. And we watched that trend expand even more when we saw like kind of the mobile wave come across, where now it's commonplace for everyone to be deployed on the cloud. On-demand hardware is really, really cool. I can spin up a slice of a petabyte box. I can take the whole petabyte box. Typically we're still doing lots and lots of like batch compute, map reduce jobs. And again, like for me, the interesting is that now open source software kind of rules the roost, where a great software organization doesn't deploy now that doesn't have at least open source roots or open source components. And so kind of the wave we're feeling now, and we'll see whether or not this turns out to be true, but I believe it to be so, is we now have this incredible confluence of incredibly cheap RAM, where we now have really, really fast disk, and then two, over here, we can actually build programmable CPUs for algorithms, so I can execute AI workloads really, really, really quickly. And we're really trying to build dynamic real-world systems, where the way we interact with and believe technology to be, or the way our expectation of technology is much more intuitive, much more human. And it's a very big difference than working with Excel. And so the way in which we argue that based on those factors, how data should be structured is this property graph model. And so rather than working with well understood structures, working with known problems that involve discrete parts of a given data set, we're looking to work with a much more dynamic system where data topology is super difficult to predict, where I don't know if a piece of information is going to be relevant or useful. I know I got to get it into the system and then have the flexibility to say, oh my gosh, this entry in this document, I got to pull that out as a feature. I want to make that really, really accessible. I want to work against it. And the requirements also on top of those systems is changing constantly. I'll say, hey, I've built a recommendation system, but the great thing is we're actually capturing what transactions are going through, and now it's an MDM system. And oh, by the way, we now need to be able to submit reports to the FDIC because of certain traceability or lineage requirements. And the last bit is where the problem set we're solving, the context around data matters. And the more that context matters, the more we want to organize that in a graph. And so the property graph model we use, or I guess invented, is broken down into three main components. We have a series of nodes. These function as kind of the discrete objects within our store. If you were to imagine all of us here building a social graph together, each one of us would get our own node. And then the relationships between us is how we provide context to that information, where I know Sean over there, and so we have this relationship together. And if we map that back to language, we can kind of talk about it as the nouns in our data. Those are going to be the nodes. The relationships will be the verbs. And if we want to describe those things, I'll store properties on the nodes to say, hey, this is Dan. He was born on this day. He has a Twitter handle. Here's Anne. She was born on this date, and this is her name. And you'll notice that our properties are actually heterogeneous, meaning I'm not obligated, to come from the relational world, I'm not obligated to store some Twitter value that is null for Anne. I'm not obligated to store it. And then we can have heterogeneous relationships where Dan can be both married to and he can live with Anne. You'll notice these are what we call reciprocal relationships, where it's implied that if Dan has a relation pointing at Anne of a certain type, it's inferred that it's reciprocal. You can't kind of have a one-way marriage. And I'm not going to touch that. And here we actually are describing the quality of these relationships. All these are kind of the adverbs to our descriptions. So we have, Dan has been driving Anne's car since January 10th. Which again, not going to touch it. The second bit is what's really profoundly powerful about the property graph model is that it maps very naturally to the way that we talk about and describe problems. And so if I were to ask someone to go, hey, can you draw out your organization? Can you draw out what we're trying to solve? That raw kind of whiteboard sketch typically actually maps relatively nicely to what we call our data model, our graph structure. And the cool thing about this is now I can actually involve the business, or I can involve the non-technical users in the decision process. Hey, how should we construct this? What are the relevant values? What are the important things for us to capture? Two, it's easy to evolve. I can very quickly say, hey, you know what? I don't think this is the right data type, and merge that into another node or push that out as a relationship. And so now I'm going to dig in a little bit on why we're building a platform and what it means to be a platform. I think the word unfortunately has been watered down a lot because everyone calls everything a platform. And so to make it meaningful, I hope we can give you our vision, tell you what we've built, tells you what we're building. And so Neo4j, since its inception, has primarily been like an OLTP database we're very focused on trying to eat Oracle's lunch, right? I mean, like transactional stores are really where a lot of business value was driven. And so our first 10 years of existence, we were focused strictly on building a best-in-class OLTP database. So we had ACID transactions. Transaction safety was paramount to us. So we said, hey, no matter what, we want to make sure when you make a commitment to Neo, it hits disk, it's safe, it's robust. We wanted to make clustering and scaling reasonable. So we started using something that we called HA. Our customers started saying, we're building bigger and bigger clusters. How do I start to handle clusters of 25, 50, 100 machines? And so we started developing something we called causal clustering. For the nerds in there, we went from essentially a Paxos protocol for consensus to something we call Raft. So we essentially ship around this really cool Raft log, and so you can really, really quickly grow these clusters. And then we built rich language and drivers and tools to say, hey, this is how to actually talk to our database reasonably. This is how to actually scale or build functional applications with our database quickly. And then the two kind of magic pieces were kind of our graph engine and our query language, the ability to, I guess, humanely interact with our database, humanely interact and say, this is what I'm looking for, can you give it back to me? And the part I really want to click on is index-free adjacency. So the business description of index-free adjacency is at write time, data is connected as it is stored. Meaning we, instead of in a relational store, you'll write what's called join logic. You'll say, hey, take this table, take this other table, find up kind of where they match and join them together. And that's done kind of at query time. Within Neo4j, what we do is upon write, we say, okay, these two things are connected. And then when we access, I can really, really quickly say, hey, show me everybody you're friends with, because it's already hard-coded into the store. We've actually created an object on disk to represent those relationships. The computer science answer is that essentially Neo4j is constructed of a series of fixed-length records. And what we then do is we utilize that fact that we have fixed-length records. And then when I say, hey, who are you connected to? My node, or the node that I'm interrogating, I say, hey, I'm connected to node 10, 100, and 1,000. And I get to then say, okay, so 10 times 33, so your friend is located at an offset in memory of 330. Oh, your friend at 1,000 is 33 times 1,000. And so we can really, really quickly essentially navigate around this little physical locations on disk. We're essentially just traversing pointers and doing arithmetic the whole time. And the magic of that is I never touch an index again. And so I go from an index operation, which is a log n operation, which is a function of the more data I have, the longer it takes me to do that operation, to a constant time operation, because multiplication always takes this exact same amount of time. And so if I'm dealing with a gigabyte of data or a zettabyte of data, my traversals are still constant. And so like a super rough benchmark that a social network could have done. So we have a sample graph of 1,000 people. Each person has roughly 50 friends. And we want to play the Kevin Bacon game, at least to some extent, where we say, is person A connected to person B within 4 hops? Are they friends of friends of friends, or whatever it may be? And of course, warm up cache. We don't want to have an I/O competition. My SQL store for 1,000 people, it's about 2 seconds. Not a real-time operation, fully loaded with latency across the wire, rendering, all that good stuff. You get about a second for a user not to feel that the application's working slowly. In Neo4j, that same operation takes 2 milliseconds. And to kind of prove out index-free adjacency, you run the same test on a 10 million node graph. There should be like a little squiggly line in front of the 2 there, where that initial index seek, we still utilize the same type of search for like the find user 1, find user 2. But then once we've seeked into those users, then we're doing that index-free adjacent traversal. And so for a very marketing-focused graph, we have no units here, but what we're trying to emphasize here is a log n operation. The more hops you're doing, the more traversals you're doing, the greater the delta will be between a native graph store and a relational store. And so the next bit I want to walk you through is the way we interrogate the graph. We use a language we call Cypher. We invented it primarily because we wanted it to be optimized for talking to a graph. We didn't want to force users to very imperatively say, okay, walk to this node, traverse in this way, do these things. And so if we were to want to match a pattern and say, hey, find me some person who lives in San Francisco. Here's our pictorial representation. We have some arbitrary node has a relation called lives into a city called San Francisco. To represent the nodes, we would draw parentheses. We would then provide what we call identifiers. These are variables. These are ways for me to continue within the query to say, hey, remember those person nodes? Give me the names off those persons. Or on those persons nodes, filter on ones that don't have a name that start with A. And from there, I then say, OK, this is a subgraph I want you to interact with. These are the labels we talked about. And then from there, I do the same thing on location. So I'm saying, find me some P person who lives in some location. And then I can describe that location or access a property off that location called San Francisco. Sorry, that is called city. And I'm looking for a string called San Francisco. And then to represent the link between these, I literally just draw an arrow, like dash dash greater than. And then I say, hey, I want to be a little more specific. It's not just a generic relationship. I want to look for the lives in relationship. And I then say, hey, match using a couple of keywords. Go find this pattern. Return me all the persons who live in San Francisco. So you guys are all now certified Cypher developers. You're ready to go. That was literally all you needed to know. And this is what I love about Cypher is it is very pictorial. It's intuitive. And when I hand it to another developer, I can say, hey, am I doing this right? It's very, very easy for them to say, oh, gosh, yeah, you're doing it terribly wrong. You're completely mistaken. And so it's a very cherry-picked example, but this is actually a SQL query given to us by one of our customers. Cisco is building their hierarchy management platform, and the question we were trying to answer for them was, for a given line of business owner, show me everybody who reports to them and everybody who reports to those people up to three hops down or three levels down. And if there are any relational developers in the room, arbitrary depth paths are really unfun to write. And we often just don't write them, right? I mean, what I do is I write a script that writes this query, and then it functions or it doesn't. And again, super cherry-picked. But this is the exact same query in Cypher, where, again, we just hold up a picture. I'm not obligated to say, hey, grab these two tables, join them, grab these other tables. I don't even need to really know what the underlying data set looks like. Just say, hey, find me some boss. That's that variable we talked about. Find me everybody he manages, up to those other subordinates, and find everybody those subordinates manage, also 3 layers down. And at the top of that tree, I want that to be John Doe. And then I kind of, in a very SQL-like fashion, say, give me the names of those subordinates and count the number of reports they have. There's an implicit group by that's handled for me, and alias that as total. And so obviously, like if I'm doing set-based operations, I'm going to want to work with SQL. But if I'm doing graph operations, I'm going to want to work with Cypher. I'm spending less time writing queries. I'm spending less time debugging queries because they're humane and I can read them. And of course, the easier to read code, and as much as managers don't care, the productivity and happiness of my developer is important. And so we said, okay, we built this really cool transactional LTP store. But the graphs, that's only like half the equation. There's an important OLAP piece. How do I take Euler's graph theory and start applying it? How do I do betweenness centralities and PageRank? Well, I need something that's very good at handling very, very large graph global operations and parallelizing them up and kind of doing those aggregate-based jobs. And our thinking here is the narrower we can make the window between build the model, build the insight, and operationalizing it, the closer we can move those together, the better for the organization, the more intelligent your system is. You can call it AI, but at the end of the day, we're doing operationalize insights in real time. The prototypical model is I take a bunch of data, I build a model, I ship that model, we put it into production, I collect all the results over time, and then 6 months later say, okay, here are all the results, I'm going to rebuild that model and push it back over. And so we wanted to do say, how do we narrow that window? And so the first step was saying, okay, gosh, we need to build data integration, make it deep, make it rich. And so when you kind of look at different integration patterns, one way is you just say, okay, shovel everything out of relational, dump it into Neo, or shovel the graphy bits. And so we say, okay, well, let's have things like load from JDBC, where I can fire a SQL query off, grab a table, and transform it over. Or how can I just literally dump a CSV file, transform it, and load it into Neo. Or you can be pulling cross silo and saying, okay, Neo4j will function kind of as like a pseudo data lake, where I'm saying, okay, I want to grab this data out of this relational store. I want to build, pull this data, the graphy data, the key value store, and will maybe function as like the metadata model, where I can then say, okay, find these things, do these things, and then go grab or hydrate this from my Mongo store. Or the last bit is where you're essentially bolting Neo4j on top of a HDFS lake, where I'm saying, hey, I want to execute graphy jobs, and again. operationalize those really, really quickly. And so we said, okay, first step in a platform is data integration. And then from there, okay, well, we need to build, again, richer drivers and richer APIs. And so we went through and said, okay, let's standardize all of our drivers. Historically, we leaned really, really heavily on our community to help build these. And actually, we still do to a major extent. But we said, okay, for most of our enterprise customers, what are the languages they're developing, and how do we make them as easy to use as possible? And so we built a series we call Bolt drivers. So we built them, and now the really cool thing, at least for those of us who have to context switch dozens of times a day, my Java driver looks exactly like my .NET driver, looks exactly like my Python driver. The forms and functions which I interact with that driver are nearly identical. I should have pulled up a few slides, but you can actually literally see the shapes transform all the way down between different languages, which again, for developer productivity is profoundly powerful. And so the next piece is discovery and visualization, saying, okay, if I fundamentally believe graphs are the most ergonomic way for people to interact with and think about data, I need to expose that to business users as well. And so, of course, we have the Neo4j browser. It's kind of a developer workbench. But we really wanted to double down on working with different JavaScript libraries, saying, okay, how do we make Viz work better on Neo4j? And the other half is looking at partner applications and saying, okay, how do we work more closely with companies like Linkurious? If you guys remember from the Panama Papers example that was showed earlier today, while those really, really beautiful visualizations were built on top of Linkurious, that would go down and query a Neo4j database. We're in Tom Sawyer, we're in Cambridge Intelligence. And so then the other half is, again, how many of you guys have actually operated a distributed system or any sort of massive multi-data center system? Okay, so my argument for having these conversations is kind of two classes of people. There are people who have run distributed systems, and there are people who think that running a distributed system is easy. It is so hard. And so again, our whole thesis as an organization is how do we do as much of the donkey work and the hard stuff, and just let our users interact with their data delightfully. And so we wanted to build really rich, administration tools. And so now for the distributed guys, we actually now essentially can do a global dump where we have the JST. I give all the debugging information you need to know, and I don't need to chase down each and every server and say, hey, give me these logs, hey, give me those logs. I can dump all that out really, really nicely and cleanly. I can administer users and roles from the Neo4j browser. I can actually take different statistics and see how's my data, is it healthy? I can do rich query logging. Oh, click too fast. And I can also start to fire and launch things out of the Neo4j desktop using it as a command center. Or I can actually from literally the doc say, oh hey, I want to pull in a GraphQL plugin such that I can then essentially build a GraphQL endpoint really quickly and easily and map that schema really nicely. I can pull in Neo4j's graph algorithms library. I can pull in Neo4j's APOC library. And our hope for this is to build kind of a graph marketplace where users can go out and grab different things and build really, really rich, cool applications, all from the comfort of their command center. And then the last bit is building out deeper integration with analytics tooling. The big data ecosystem is so incredibly rich and powerful. We wanted to ride on the coattails of that and say, hey, how do we enable our users to deploy that? And so if you guys are unfamiliar, Apache Spark is one of the best-in-class big data analytics toolkits writ large. And so we wanted to say is when talking to a graph, you should always use the same language. The best language in the universe for that is Cypher. And so how do we deploy that? And so we actually worked with Databricks and the Apache team to say, let's make sure Cypher gets out there. And so now you can execute Cypher over a Spark cluster and essentially compositionally stack graphs together where I can say, hey, go grab stuff out of my Hadoop store, go grab stuff out of my relational store, and grab some stuff out of Neo4j, compose those in memory, transform it, work with it, and then go persist it in Neo4j or go persist it back in my whatever my other store is, and really quickly and easily work pass data back and forth. And again, on the algorithm side, we wanted to again enable users, and so we said, okay, let's take the algorithms that don't work well as a map or essentially as a distributed job. There's certain algorithms that map best to being held all together, where I'm working against the entire graph. And so actually Ryan will be talking a lot about this. I don't want to steal his thunder, but we built lots and lots of really cool stuff with it. primarily like deploying things like centrality metrics. How do I figure out who is the most important graph in my node? Who is the most dependent node in my graph? How do I identify cliques and clusters? How do I find the fastest way between point A and point B, traversing through 100 million nodes? And I guess one more thing, right? I mean, like what is a data platform if not cloud enabled, right? And so we're, for people who are attending the Neo4j Graph Tour, we're very quietly starting to let people into our Neo4j Cloud beta. The hope is to help users kind of like jump that impedance curve of learning Neo4j and operationalizing it, and to lower the cost of entry so you're kind of paying as you go. And so the solution we built is Neo4j as a service on a public cloud. People who need other types of clouds, sorry for now. Automated backups, automated upgrades and restores. And so if you'd like to join, neo4j.com/cloud for our preview. It's not production ready, but it'll at least give you a flavor for what we're building. And please give us rich feedback. Tell us what you love, tell us what you don't love. And I guess I won't leave you. So what I will leave you is kind of, at least to me, why we're building the graph platform. I wholeheartedly believe this, that graphs are fundamentally like the most ergonomic and humane way of working with data at scale. Graphs are the way in which we think. And to enable and deploy that for people, like I want to see that happen in the universe. Two, I mean, ecosystems, the more open an ecosystem is, and the tighter the integrations are with the adjacent technologies, the stronger and richer that ecosystem is. And the last bit is the easier we make our technology to use, the better we make our technology for our users. That's how we win. That's how we get graphs to be kind of back to point one, the ubiquitous data structure. Cool. So thank you guys.